So let's talk about the hypothesis here. Let's start right there. What Dr. Mossbridge found is that there's a correlation, or at least there can be, it's been found in some experiments, there's a correlation between pre-decision and post-decision data in an experiment where there's a decision about how long that experiment will run. So in other words, as you can see, the little X's down here are data. I can point with my mouse. Little X's down here are data. And each time the experiment runs a trial, and it ran about 34,000 of these trials, each time it makes a decision where this vertical line is as to how long the remaining duration of the experiment will be. And that remaining duration seems to affect somehow the data that either came before that decision or the correlation of that data before the decision with the data after that decision, but still dependent on how long the trial goes on for. So in order to make a comparison, we have to have some data after the decision to compare to the data before the decision, but the remaining duration after that matters for that correlation. Well, I'll get into that in more detail. And you'll see this slide again. I'm going to bring it up 2 more times in this talk in different variations. So let's talk about what Julia Mossbridge found and what her protocol was and what she means by what we mean by causally ambiguous duration sorting. So the experiments that she reported on in 2019 and 2021 all involve these elements on the right. And here's a plot from one of her talks. So the light source, it involves a light source and a detector and photon counting. And the light source and detector are both turned on and off as for each trial. So when a trial begins, the light source and detector are turned on. And when that trial completes, light source and detector are turned off. They stay off for 3 minutes, and then they turn on again for the next trial, which might have a different duration or the same duration as the previous trial. And then the average photon counts, as I mentioned, show a dependence on the future random duration. And the time scales involved are seconds to minutes. And what you can see in this plot here, the reason I'm showing this, is that you can see very clearly here, the yellow curve, which is a average of long duration runs, is distinctly different than the green, blue, and you can see a little purple curve here, which are shorter duration runs. And that difference between those longer and shorter duration runs doesn't just appear at the end of the run. You see a difference in the earlier part of that, of those runs when averaged, even though that that decision hasn't really been implemented in any difference here. And actually, even before the decision is made here, the red line is that decision about how long the duration will be. Even before that decision is made, Dr. Mossbridge found a difference between the longest duration trials and the shorter ones. So we want to follow that up. So the current experiment that I've run for, it's actually just completed 2 days ago, it completed a year running, but the data I'm reporting is just through February 21st. There were key differences and upgrades in the hardware. The photon detector, instead of a photomultiplier tube, is a single photon counting module. In other words, a reverse bias diode. The pulse counting is done by a field programmable gate array, which is independent of the computer. There's random number generation, Julia and I are quite excited about, that is a big upgrade, and I'll tell you more about that later. I used LabVIEW instead of MATLAB, and all the code and everything was all independently written. She had told me her protocol, but I hadn't worked with any of her code. And to ramp up and down the voltage for the inverse bias of that diode in the photodetector, I used an RC circuit for that. There was an RC circuit already in the box that I had for operating that photodiode. And what I did is jumper in some circuitry so that the computer could turn it on and off instead of a manual switch. And then the experiment was operated continuously 24/7 for over 6 months, whereas Dr. Mossbridge's experiments were usually run for maybe 5 hours a day. Okay, so let's look at the optics. As I mentioned, it's a photon counting experiment. Our photons begin here from this light emitting diode. This is turned on and off by the computer software in LabVIEW. And then it hits a diffuser so that you get an even, so like even if the LED were to move a little bit, it wouldn't affect the counting that much because it's being diffused here. And then it goes through some miscellaneous optics that just happened to be on the table and I didn't see need to remove them. And then this is important. It goes through this detuned bandpass filter. What I mean by detuned is the bandpass filter is designed for infrared photons at 880 nanometers, but this LED is around 650. So most of the light will be blocked by this. That's important because it gets us down to a low counting rate. And then the photons that are coupled into this fiber coupler go to the single photon counting module, that reverse bias diode that I mentioned previously. So it's only about 3,000 counts per second we're getting here. So that's a low enough rate that it seems appropriate for this kind of experiment. Okay, so let's look at the whole overall experiment. So this is the optics part. And you see the optics part is shown here with this red line. That's representing the light coming from the light emitting diode to the single photon counting module. Here's the field programmable gate array I mentioned. It is controlled by the computer, but it counts autonomously and then feeds that data back to the computer. The single photon counting module is also powered. It's powered by this power supply that I mentioned that has a resistor capacitor circuit that ramps the voltage up and down. That's so that the inverse bias diode is a little bit gentle, just like a phototube. So you need to ramp the voltage up and down. And there's an optical isolator there. That's just to avoid ground loops, right? Because you have a connection here, you have a connection here, and you have a connection here. You don't want to have a ground loop. So I put an optical isolator there just to avoid that. And then it's all controlled by this LabVIEW program. It controls the LED, controls the counter, and it controls the turning on and off of the detector. Now, where do I get my random numbers to determine how long each trial is going to be? That comes from this whole system down here, which is completely independent. It's not a computer. It is hardware implemented. And this is the upgrade in the random number generator that I said that Dr. Mossbridge and I are so excited about, and I'll tell you about that next. So actually, let me point out before I go to that next slide that there's a photomultiplier here. This is independent of the photodetector here in the single photon counting module. This is an independent photomultiplier attached to a big tank of scintillator oil. This thing is big. It spans between 2 levels in the building. And then it goes through some amplifiers and threshold discriminator, and then it hooks up to a pseudo-random number generator. But the numbers that are generated aren't just pseudo-random. It actually incorporates the true randomness over here. And I'll explain how that works as I go through those next slides. So this is the top end of a photomultiplier tube. It's pretty big. It's like kind of the size of a watermelon. And the photomultiplier tube is down below. And then down below that is tank scintillator oil supported by these steel beams. And when stuff happens in the atmosphere or nearby, you may get a particle that passes through that tank. You get a flash of light that gives you a pulse out of the photomultiplier tube. And because it's a pretty big tank, we get about 40 hertz pulse rate out of this. And this provides the true randomness for our random number generator. Then, to get uniform likelihood in the numbers, those true random pulses are used as the clock inputs on each of these integrated circuits. These integrated circuits, these CD4015s, are 8-bit shift registers. And I can talk more about this when we get to Q&A, but I enjoyed building this circuit. And basically, the pseudo-random numbers are advanced to the next random number each time there's a detection in that tank of scintillator oil. So when there's a detection in the tank, then you get an advancement to the next number. And because those detections in the tank are happening at about 40 hertz, about every 2 seconds, you get a whole fresh 80 bits here in these random bits. And that's used right here. 2 bits of that information are collected by the LabVIEW system. And like I said, these are independent. So the LabVIEW system doesn't know what's going on. There's just 2 wires connected from that hardware circuit to inputs of the LabVIEW system. And they're just literally 2 jumper wires like that. And the LabVIEW system simply says, I want to read these 2 digital inputs, boom. And it gets a random pair of bits and uses that to determine what the duration of the trial will be. Let me go through the whole trial. So each time a trial occurs, the system, let's say, is off initially, right? When that trial begins, there's a warm-up period after the photon counter and photon source, the LED, are turned on. That warm-up period lasts for 6 seconds in my experiment. That's different than Dr. Mossbridge's experiment. My system requires the 6-second warm-up. And then there's 3 periods of counting of 11 seconds each for the photons. So that's when you see on those plots, those 3 dots at the beginning, you'll see that again. That's, or the 3 X's, that's those 3 counts that occur in every trial, regardless of the random number. Then, depending on the random number that's chosen, you either have 0, 20, 30, or 60 additional counts. So those would be 20, 30, 60, or 0 additional 11-second periods. So this whole trial can go on for several minutes, after which there's a 3-second off time where both the detector and the source are off before beginning again. And that's a key feature of the experiment that Dr. Mossbridge did and seems to be key to getting this to work. And so I replicated that in this experiment as well. So let's look. This is the second time you've seen this before. I started out this with my first slide, but I'm pointing to different things here. So I was just talking about how the random number chooses how long the trial will go on for. And you can see here, the random number chose that the trial would go on for 0 additional counts. And you see there's just those 3, right? It just did the 3 initial counts. You'll see it says here times 10 to the 4. So this is about 30,000 counts in each one of these bins, right? So there's 3 bins of counting before the random number. And then at this point, the random number said, we're not going to go on. So, okay, fine. Here, the random number said, we're going to count for 20 more times. And here, 30 more. Here's another 20. Here's another one where it just counted for 3 and then stopped. And here's one where it went on for 60 additional bins. So the trials have a minimum of a 3 and a maximum of 63 measurements. So here's what the data looked like over the whole 6-month plus period of time. We completed 34,454 trials for a total of 1,047,902 of those 11-second measurements. And so there's a dot on this plot for each one of those 1 million measurements. You can see there's quite a lot of interesting features in this data. There's sort of a general downtrend. There's a daily variation. And actually, if you look under that, there's actually a twice daily variation. You can't really see here. But these little bumps you're seeing, you know, 1, 2, 3, 4, 5, those little bumps are each 1 day. This is about 210 days of data. There's also this sort of larger movement about every 25 days. There's these kind of larger movements and dips. And these are not particularly correlated with times that I went in the room to back up data or anything like that. This is one continuous run of the experiment that's actually still was still running until Tuesday when I shut it down. So the computer was not restart. The software was running continuously. All the hardware was running continuously. There were no power outages during the whole time. You can also see there's interesting things going up here and going down here, which I'll talk about in a couple slides later. I want to point out that there's a really big change in the data right here, that up to here, it's kind of sort of a similar pattern, and then the pattern really changes. I'll talk about that in the next slide. So Dr. Mossbridge noticed that, you know, just looking things up online, like what happened on the 17th of January, and she looked at some newspaper headlines, and there was this headline about officials being pegged as, for stuff. And that was a major flashpoint that didn't turn out to be a big flashpoint, but there was a lot of energy, a lot of concern about it. And so maybe emotions affect these things like they affect the Global Consciousness Project. There's also striking situations where you don't see anything. Here, September 22nd is the fall equinox, and here's the winter solstice on December 21st, and there's no particular thing that seems to be happening there. But there's other ones like Election Day, November 3rd appears to be just right before there's this significant change in the data. And these could just be coincidences. Maybe this is when the weather changed or something in Berkeley. So this is interesting, but it's not the main focus of this talk. So I'm going to set this aside for now and get back to the main focus, which is looking at the correlations within each run, within each trial. So in order to deal with these things that are really outlying here above and below, I did a removal of low frequencies. And I used a fast Fourier transform filtering to remove low frequencies. And I removed frequencies that are daily variation, and I removed the twice daily variation that I earlier mentioned. And I even removed the variations a little bit faster than the twice daily variation, just to make sure I sort of got it. And that smoothed things out very nicely in this orange curve and makes the outliers really easily visible. You notice the outliers are not just single points also, that they tend to be groups. And so I used that in noticing what are the outliers and setting them aside. You'll see later I do the analysis with and without the outliers, and the results are actually fairly similar. But this was one of the initial things I did, was to identify outliers. And so there's my outliers. There are approximately 1,000 outliers in the whole million counts, but they cluster in about 64 out of the 34,000 trials. So they're pretty heavily clustered. And so can be fairly, you just remove those trials and it's pretty straightforward, since we're doing a trial by trial approach in the analysis. Okay, now this is the third time I'm showing you this slide. I've changed things a little bit. I'm calling attention to the trials that have data after the decision. So remember, there's a decision here by random number as to how long the trial will go on, whether it's going to go on for 0, 20, 30, or 60 counts. However, I'm paying special attention to the ones that have at least some counts after the decision, because an analysis approach that Dr. Mossbridge came up with utilizes a correlation between those before and after the decision. Okay, so here's a schematic of that analysis that Dr. Mossbridge came up with and that I implemented in MATLAB. So the data is first divided by days. So there's 210 days over which data was collected. And so for each day, we look at the pre-decision data on the trials, and we look at the post-decision data on the trials. And we average over actually just 2 of the 3 pre-decision data counts, and we average over all of the post-decision data counts. Okay, those averages form an XY pair in some arbitrary space for each trial. Okay, so now what we do is, depending on the duration of that trial, we sort those XY values so that they contribute to either an average of the 20. So in other words, all the X's for the 20 duration trials get averaged, and all the Y's for the 20 duration trials get averaged. That forms this X20, Y20 pair. Same way for the 30s, same way for the 60s. So we have 3 XY pairs, and we do a correlation, and we get the rho value, or we're just calling it R here. And that R value then gets averaged over all 210 days. So we get 1 R value for each day, and then we average those 210 R values. And what we find is a rather strong correlation. The average correlation is quite strong, and that's shown by this line here on the graph, almost 0.75. On the other hand, if we take each XY pair and contribute it instead to a random XY, so even though the actual duration might be 20, it might be that XY average might be contributed to the X30, Y30 pair, for example. Okay, and we do the scramble in such a way that we preserve for each day the number of X and Y that contribute to the X20, Y20, and the number that contribute to the X30, Y30, and the number that contribute to the X60, Y60. So we preserve how many trials contribute to each. And if we do that correlation, we get, again, 210 R values, one for each day. And then averaging those 210 values, we get a much weaker correlation. And that's demonstrated by doing this scramble 40,000 times, 40,000 different random numbers. And then that forms this histogram here shown, which forms quite a rather nice bell curve. So I'm going to move to the next slide. So here, this is that same plot I just showed you, but just bigger. And here I'm calculating a sigma for the original assignment, the correct assignment of the data by duration versus the scrambled assignments. And so the way I've done that is to take the original R value, the correct assignment R value, subtract the R value for the average of the scrambles, and then divide by the standard deviation for those scrambles. And that produces a sigma of 5.69. I mentioned earlier that this is pretty robust to outlier removal. So if I put those outliers back in, like just ignore that part of the presentation where I talked about outliers, then we get a sigma of 5.27. It's not changed all that much. This is so far the major result that we've come up with. It's the strongest result so far, and we're still doing a lot of analysis to figure out if we can come up with something better in addition to this. But in the meantime, Dr. Mossbridge has also looked at some day-night variation because remember the experiment she did, she only measured during the day, and I'm measuring day and night. So that gives an opportunity to compare those. So I'll show that in the next slide. One of the things that, these are slides generated by Dr. Mossbridge that I've put into this presentation. One of the things that she noticed is that there's a significant difference between day and night data. So looking over the whole 6+ months of data, and this is sort of, it's sort of significant, sort of in the noise. We're not claiming the significance of this at this point, but you see that there's this kind of interesting reversal that nighttime data has kind of an opposite character to daytime data in a certain way, in how the data separates by trial duration. We see that again here. So horizontally are 3 different comparisons here. This is the what I call the 20s, where there's 20 counts after the decision. And this is the zeros, where there's 0 counts after the decision. You can see the comparison there. And then at nighttime, you get the reverse of that. Well, I should say this is data before the winter solstice. So I'm going to show you 2 charts of 6 plots each, before the winter solstice and after the winter solstice. Okay, so this is the first of 2 slides before the winter solstice. And you can see that there's this reversal, right? And here, again, more showing the reversal. Okay, now after the winter solstice, look at this. This is in the same direction instead of reversed. So this is just really a curious thing. Like, we don't know what this is about, but it seems like something to investigate further. And here's the other plot showing that as well. You can see here, maybe there's some, it's not quite reversed. Maybe there's a different frequency of fluctuation in how these things relate to each other for some curves relating than others. So to sum up, this has been a replication and extension. The apparatus has been upgraded. I've run day-night collection instead of just during the days. It's possible that there's sensitivity to astronomical or emotional events. That bears further investigation. And there's a lot of work to do in understanding these causally ambiguous duration sorting and why that's happening. So I'll close there and ask questions, please.
Thank you so much for that really interesting presentation. We've got quite a lot of buzz in the chat, so I'm going to go through some of those questions and hopefully we can get through some of them in this time. Let's see. So the first question is about whether any of the variations in counts could be correlated with sun activity, like sunspots or flares.
Yeah, there's a slide here about geomagnetic fluctuations right here. I haven't really looked at this, but that would be a good thing to look at. Yes.
Could I add to that just briefly?
Yes, please.
So not only are there geomagnetic, or these are geomagnetic field fluctuations with the seasons. You know, the Earth is in this little spot in the middle, and so clearly, even within each season, well, not clearly because you can't see, but the sun is over here. I don't know if you can see my mouse.
No, can't see your mouse.
Yeah,
the sun would be over here.
Right, exactly. And so at nighttime, that's flipped. So this shows the seasonal, and by inference, the day-night difference. So there could be a whole geomagnetic effect that could happen on the electrons in the detector as potentially as well as the medium that's containing the photons.
Thank you.
Yes, thank you. Very fascinating. Next question, are you planning on exploring any pre-registered event correlations with these data patterns as with the GCP data that we know more about?
I don't know what my plans are with this next exactly, but that could be a good idea. Yeah.
Yeah, it seems really...
I would like to say, like, this, we just discovered those very recently, and that wasn't the main point, but there's a lot of work to do.
Yeah, it's very interesting. Let's see. Do you have any information on what causes the diurnal variation? What about the steep dips that seem to come more or less regularly, especially in the first part of the data, many days apart?
I don't know what the steep dips are. I kept track of when I would go in the room to upload data and stuff like that, or when I had the lights on. There was one time where the lights got changed, and so other people were in the room for a little while changing the lights. And that's not strong. That, you know, maybe one of the things is due to that, but that doesn't seem to be a major cause. As far as the diurnal variations, could easily be temperature. You know, almost any instrumentation will vary with temperature. For the latter half of the year, I've now been running with a thermometer in the room logging. So we'll see if that is correlated.
So watch this space.
Yeah.
Yeah, this is very interesting. It's very hot off the press as well. There was a major increase in sunspots and solar flux in November to December. This person says it might be interesting to look at solar weather correlations as you go forward.
Yes, I think that's a good thing to look at.
Yeah, maybe you could look at that actually, because who was the one who asked the question? Doug?
That was Doug Richards.
Yeah, Doug, talk to us maybe. I mean, we need someone who knows what they're doing there.
Yeah, that'd be great.
This is the purpose of this conference, to make connections and get some insight, so that's great. Another question from York, can you use the correlation measurement between the pre-decision measurement and the first 20 post-decision values to predict whether the remaining duration after 20 trials is an additional 0, 10, or 40 trials? And with what statistical confidence can you make this prediction?
I haven't come up with a way to do that. I don't know if Dr. Mossbridge has.
Yeah, I'm working on that. That's not in this paper, but that's obviously an interesting topic.
Yeah, lots of fascinating possibilities here. Can you both say anything about what the next steps are then with this research agenda? What are you planning next?
Well, like I said, we've got more additional data logging running since February. We'll see if that tells us anything. we've got that whole set of data that I haven't looked at yet. I've just been uploading it and backing it up. There's lots of different ways we could set up photon counting. And it may also be interesting to look at fermions instead of bosons. So if we were to count electrons, would we get a different result?
Julia?
I think those are interesting questions. I think there are also interesting questions about when the knowledge, like playing with when the knowledge of the duration occurs, sort of an ontological versus epistemological sort of interpretation of quantum mechanics type of differentiation. I think basically publishing what we have. So the first paper that I have out there and the conference proceedings are on like crappy equipment, and Wind just made it so much better. And so I'm just grateful that I was actually looking at something real and not an artifact. And so that's exciting, and sort of uncovering it more. I think these seasonal day-night variations are profound, and especially not just the overall in the overall data, but in the actual relationship between the durations. I think that the relationship between the durations, I imagine kind of like different weighted ropes and oscillating at different frequencies based on the weight, and the weight is set by the duration sort of. And so I think that that's how I envision it, with no actual data, but just sort of living with this experiment for a couple of years.
That's a good
Yeah.
answer.
Yeah, I'll add that the random numbers in this experiment are selected once for the choice of the 4 durations. It would be interesting to try having the first random number just select whether the experiment concludes at that moment or not, and then draw another random number to determine what happens next and whether the duration goes on longer. And then between the 30 and 60 choice, draw another random number. Yeah.
Yeah, and there's some indications that if you don't choose a random duration, in other words, at least this is different. We didn't show you this data, but I'm just telling you based on my own observations. If you don't choose a random duration, you actually might not get this duration sorting effect at all. So it might be that there has to be a choice.
Mm-hmm.
Fascinating stuff. Thank you once again for this really hot off the press, interesting talk.